IBC Calc, we're up to your day 91 notes. Today we are extending our concepts of integration by parts to double integration by parts. So we're going to do some more just single integration by parts to get started today, and then we'll eventually build up and see why we might need to do it twice. So here's a quick example that I'd like you to try on your own. Evaluate that definite integral, 2 to the ln x over x dx from 1 to 2. And then there's another example down here I'm going to give you a hint about, but I would like you to try this one as well. See if you can CTS. Do you know what CTS stands for? If you don't know my abbreviation for it, complete the square. Okay, complete the square there. That should help you, lead you in a good direction to be able to evaluate that integral as well. So try those two. We're going to jump right into the next page of the notes, which is more integration by parts. We can now find, using integration by parts, the integral of ln x. And if we think about setting up our u and our dv columns for our differentiate and our integrate columns, we certainly can't put our dv as ln x dx because we don't know the integral of ln x. So that's going to have to go ln x in the differentiate column, which means that dv is just going to be dx here. Okay. So if I have that as u dv, the original integral, then du over here is going to be 1 over x dx. And then dv would make that v would equal x over here. So I gave you the general rule for integration by parts again. It's going to be u times v minus the integral of v du. So if we go ahead and rewrite the substitution here, we have that the integral of ln x dx is x times ln x for u times v minus the integral of v du, so x times 1 over x dx. Okay, so that's just x ln x minus, well, here the x's would cancel, so I'm just left with 1 dx. And the integral of dx is going to be x, so therefore we get x ln x minus x plus c, final answer. And if we think back, I believe I gave you this example as a derivative to calculate once, and we found that the derivative was ln x. So in thinking about, okay, now we have a technique to find the integral of ln x to get to this result right here. But of course, if you were ever unsure, like, did I actually do that process right? Find the derivative. Go ahead and check it. As a quick follow-up to that, if I gave you the same integral, but I made it a definite integral from 1 to e, if I use what we just found to be the integral of ln x of x ln x minus x, plug in the upper bound of e and the lower bound of 1. When I plug in the upper bound of e, I get e times ln e. Well, ln of e is 1. So e times 1 minus e, that's just 0, isn't it? Minus, when I plug in 1, 1 times ln of 1, well, ln of 1 is 0. So that's going to become 0. And then minus 1 over here. So it's actually 0 minus negative 1 for a total of positive 1. And maybe that actually makes sense now because we defined E, one of the 3 ways that we defined E way back when, is it's that upper bound of integration here of the function ln x such that accumulated area totals 1. So that confirms that result now that we know how to find the antiderivative of ln x. Well, the great thing is that we can use this same approach to now start finding antiderivatives of things like tan inverse. Okay, so a few days ago, I gave you a list of functions that we didn't know the antiderivative of, but integration by parts really to save the day here. When I think about my differentiate, my integrate columns, similarly to what we did with ln x above, we're going to let u equal tan inverse this time, and then dv equal dx. So if u is tan inverse, I know that du is 1 over 1 plus x squared dx. So I'll just put the dx up in the numerator there, over 1 plus x squared. And then over here, v would just equal x. So if I follow the pattern for integration by parts, the integral of tan inverse dx would be u times v, so x tan inverse x, minus, and then we're going to get v du, so it's going to be x over 1 plus x squared dx. All right, so now we have to evaluate this integral, and the nice thing is that we can evaluate this integral by using some u sub, right? If we let u equal the entire denominator, 1 plus x squared, then du winds up being 2x dx. So we can use a nice u substitution here because we have x to 1 less power up in the numerator. And I know that u is going to give me my du to be that 1 less power as well. So therefore, this turns into x tan inverse. And let's see, if I multiply both sides by a half, that's going to keep this balanced. So it's minus 1/2 the integral of 1 over u du, which, look what's coming back into play now, x tan inverse of x. This is going to be minus 1/2 of ln absolute value of u. And then last but not least, if I replace u with 1 plus x squared, it becomes x tan inverse minus the ln of, when I plug 1 plus x squared in there, we don't necessarily need the absolute value anymore because that's always a positive amount, over 2 with a plus c. So, I mean, pretty wild stuff here. I don't know if we necessarily anticipated that when we started off, tan inverse will wind up having natural logs as part of its antiderivative, but look at where we are now. All right, so this is a way to generate the antiderivative for tan inverse using some integration by parts. We might even see sine inverse sneak its way in the next few days as well. Very similar technique. Okay, let's take a look at when we might need double integration by parts. Here's an example of what we'll see with double integration by parts, and you'll see why in just a moment. But if we start with our typical approach of saying, all right, what are we going to differentiate? What are we going to integrate? Okay. Let's start by saying that we're going to differentiate, let u equal x squared, and we'll let dv equal e to the x dx. All right, so on this side, the differential column is du would be 2x dx, and then the integration column is going to be v equals e to the x. All right, so with that initial integration by parts, we're going to wind up finding that this is u times v, so x squared e to the x, minus v du, which is the integral of 2x e to the x dx. And if I look at the integral that I'm left over with, this integral, we do not have a quick u substitution, like let's say we did in the last example, that's going to take care of this. If this was something with like e to the x squared in it, maybe that would have been okay, because then a u sub for the exponent there would represent our du on the outside. But what we're going to have to do in this case is, as the title implies here, let's just do integration by parts again with this integral, and we'll continue to break it down to eventually get the antiderivative of x squared e to the x dx. So it doesn't really matter to me. I guess if you use u and v again, sometimes you'll see different variables used when we do it a second time. So maybe we'll do like w and z. I don't know. Let's go wild, guys. So I'm going to let w equal 2x, and therefore dw would be 2 dx. Over here, the integration column, I'm going to put dz as e to the x dx again. And we know that z, therefore, is e to the x. So if I use integration by parts here, it would be w times z minus the integral of z dw. All right, hopefully the w's and z's aren't throwing you off here. But if I bring back what I have over here, it's x squared e to the x minus, now remember, this is going to be a whole new integration by parts with uv minus v du, or wz minus z dw in the integral. So that's going to be minus 2x e to the x, and then minus the integral of z times dw, which is 2 times e to the x dx. Okay. So now that we've got this down to a constant and there's no more variable left next to this, we can now find the integral of 2 e to the x fairly easily. It would be x squared e to the x minus 2x e to the x. And then this would just actually be minus 2 e to the x. So last but not least, if I kind of just distribute the negative through, we're going to wind up getting that the original integral x squared e to the x dx is equal to x squared e to the x minus 2x e to the x, and then that would become a plus 2 e to the x. Don't forget about plus c. If you're looking for alternate forms, these actually all have e to the x in common, so you can factor out an e to the x from all three. But otherwise, this would be an okay form to leave your final answer in as well. Okay. So don't be afraid if you do integration by parts once and the integral that you're left with still doesn't have either an easy integral to find or an easy u substitution. Do it again. Okay. You can do integration by parts really more than twice, even if you really wanted to. You could do it 3 times. You could do it 4 times. I mean, that's going to get pretty tedious if we have to do it more than twice. So for that reason, I'll offer up another method for you. And I think you're going to like this when you see how much cleaner it looks. And it's something called tabular integration. Now, tabular integration is a way to determine an integral where you have one part of your product that is polynomial and essentially eventually turns into a derivative that would be 0. Okay. So that's kind of a hint. And then the other part of this is actually going to have the same integral throughout. So if I think about my columns of u and dv here, if I start off with u equaling x squared and dv equaling e to the x, what we're going to do is we're going to differentiate this column. We're going to find the antiderivative of this column. And we're going to keep going with my u column until we get to a 0. And that's going to happen fairly quickly here, right? The first derivative would be 2x. Integral here would be e to the x. Next derivative here is 2. Integral still e to the x. Then finally, third derivative here is 0. And then the integral still e to the x. So how do I take this list and translate it into the answer that I know this integral to be? Well, we're going to do this special scenario where, and I'm going to offer this up without proof. So for those of you interested in the proof, go ahead and look it up. We're going to diagonally multiply and switch signs along the way. I'm not sure why, but it kind of reminds me of a similar feel to when you find the determinant of a 3x3 matrix. Maybe you'll agree with me as I start drawing these lines, but I'm going to diagonally multiply those, and those. I don't really have anything to pair up with the 0. And the signs that are going to go in front of those are plus, minus, and then plus at the end here. So it starts off as a positive product always, and then the signs alternate as you go down that diagonal multiplication. So let's see if that matches. So it's going to be x squared e to the x for the first term, and then minus 2x e to the x. And the last term would be plus 2 e to the x with a plus c because it was indefinite. And that's exactly what we have up here. So some of you might be saying, Mr. Hall, I'm not going to even question you. I love this method. Now, tabular doesn't always work. But if you notice that we have this pattern that it's going to require multiple integration by parts, and one of those products is going to go to 0 as you find its derivative, that's a quick way to approach this technique here. Be able to come up with the integral pretty easily. So both methods work. If you forget tabular integration and the pattern for the signs, go right to double integration by parts. Okay, but notice how it does get you the same exact result. Let's try another one. So here's x cubed sine x dx. If you're looking at this one, are we thinking whether or not it's a good candidate for tabular integration? I don't know. I think I might like it. I mean, we have this polynomial here, u. I'm going to put that as x cubed, my dv column. I'm going to put sine x. You know, the dv column, you want to pick something over there that is fairly easy also to integrate, right? I mean, if we have to go a couple of integrals out, we don't want to deal with something that is going to be messy to integrate there. All right. Okay, so as I go down the line here, if we start finding some derivatives, we know this is going to be 3x squared. We know that turns into 6x, and then that turns into 6, and then eventually we do 0 out on this side. Okay. So then from there, if I'm thinking about finding the integral on this side, so the integral of sine x is going to be negative cosine x. The integral of negative cosine x is going to be negative sine x. The integral of negative sine x is going to be negative cosine x. And the integral of negative cosine x is sine x. Okay, so if I connect these, Did I mess up a sign somewhere here? The integral of sine x is negative cos. That makes sense. The integral of negative cos is negative sine. The integral of negative sine is, sorry, this is just positive cos, isn't it? Okay. All right, so sorry, that should be a positive cos, right? Integral of negative sine. And then the integral of cos is sine. So that's good. Okay. All right, so now that I have that, we're going to go ahead and say, okay, this is the positive product, negative, positive, negative. Alternate those signs. So then the first term for my integral is going to be negative x cubed cosine x. And then when I negate this negative here, it's going to become positive 3x squared sine x. Here we're doing positive, positive, so plus 6x cosine x. And then finally at the end, oh, I can run it out of room here, minus 6 sine x, and then a plus c. Okay, so I think you'll like this technique better. I mean, think about how many integration by parts you would need instead of this tabular form, right? So I think it's going to be to your benefit. You're not going to have a u substitution. If you let u equal this and dv equal this, you're not going to have a u substitution that's going to work until you do integration by parts, 3 to 4 times there. So definitely a cleaner technique, something to think about and consider when going through and finding some integrals. All right, last one is e to the x cosine x. So for this example here, if we were trying to approach this from a tabular integration perspective, if I let, let's say, I don't know, u equal e to the x and the dv side equal cosine x, you're going to run some issues, aren't you? Even if you switch it and let u equal cosine x and dv equal e to the x, there's going to be issues with both of those columns because both of these are cyclical functions. So when you have two functions that product are on the inside, you can't use tabular integration because you're never going to have one of those zero out there, kind of like we do with the polynomial there. So, I mean, you could start it off, and if you're unsure, and be like, let me see, but this is going to be a whole column of e to the x's, and then this is going to rotate between sines and cosines and all those good things. So we are going to have to do double integration by parts. There's no tabular that's going to work here. But there's going to be a trick at the end, and it's a pretty nifty trick that's going to allow us to find the antiderivative. You'll see what I mean by swing it when we get to the very end. All right, so I'm going to let u equal e to the x and dv equal cosine of x dx. All right, so over here, du is going to be e to the x dx. And then over here, if I take the antiderivative of cos, that's sine, so v is sine x. Okay, so in the very first step, we get uv, so e to the x sine x, minus integral of v to u, so that's e to the x sine x dx. All right, so now I'm looking at what's in here, and I'm like, well, I can't quite find the antiderivative of that easily, so we do need some integration by parts again. So let's do, I don't know, let's let w equal e to the x, so therefore dw, e to the x dx. I'm going to say that dz is sine x dx. If I can squeeze that in there. Okay. And the integral of sine is negative cos. All right, so if I use integration by parts here, it's now going to be e to the x sine x minus, let's open some brackets here. It's going to be negative e to the x cosine x minus the integral of these two multiplied, so that's going to be negative e to the x cosine x dx. Okay. So this is from the first integration by parts. This was then this integration by parts here. I'm going to go ahead and pull out that negative here and make that a plus on the outside. Because here's what I'm going to write in the next step. So if I pull out that negative and make this a plus sign, I'm going to bring back that the original integral I'm trying to find is e to the x cos x dx, and that this equals e to the x sine x. If I distribute that negative in, this is going to become a plus e to the x cosine x. And then now that this is positive here, distribute the negative there, it's going to be minus the integral of e to the x cos x dx. Now, at this stage in the game, if I'm looking at this integral, is this one easy to find? No, I mean, this is just going to keep going and going. Both of these are cyclical, right? So we're never going to get to a point where we don't need integration by parts if I just keep going and going and going and going. But I want you to stop and take a look at what you have right here. All right. So I cleaned up the signs on this side. Here's what the integral is currently equal to. We're not going to do integration by parts again here. But notice how this integral is the same as the integral on this side. So here's what we're going to do. Watch this. Ready? Follow the dotted line all the way over here. We're up to the step where we get to swing it. Okay, so you're going to take this integral, swing it to the other side, because if I have integral of e to the x cos x plus another integral of e to the x cos x, we now have two integrals of e to the x cos x dx. That is so cool. So then that equals e to the x sine x plus e to the x cosine x. And then the last step to figure out what our original integral is divide the two over. So the integral of e to the x cos x dx is equal to e to the x sine x plus e to the x cosine x, all divided by 2. Wow. Okay. So if you have two functions that are both cyclical, think of this as a pattern that we still needed integration by parts twice, because we had to eventually get an integral here that matched the original. That's when you get to swing it. Okay, so swing this to the other side. We now have 2 of those. And then dividing that 2 back over, that's a really neat and nifty way to be able to find this antiderivative when it appeared like, uh-oh, integration by parts. Just going to leave me in circles here. Just as a quick consideration, what if from the start we had let u equal cosine x and then dv equal e to the x dx? What do we think would have happened if we had switched it? Well, probably no surprise that we would get exactly the same results, right? Maybe it would look slightly different, but in the end, we would be able to generate the same exact results if you had switched it from the very start. So I think that's pretty awesome. All right, we'll talk a little bit more about this next time in class. There are some AP questions that follow on the last page that I'll have you work on in class next time I see you. So these are going to involve some derivatives and antiderivatives that we now know and are pretty well versed with. So hang on to those 1979 AP questions, and we will do more practice with double integration by parts next time I see you. Have a great day.